We'll come to the talk about prioritized constraint-aided dynamic partial order reduction. My name is Jie from SATD Laboratory of Xidian University. In recent years, program verification is widely used in software engineering to improve the quality of a program. Some verification techniques, like model checking, explore the reachable state space to prove the property or report a counterexample if the property does not hold. However, when verifying concurrent program, thread alternation aggravates the verification difficulty since the non-determinism of thread scheduling will significantly increase the traces to be explored. In order to reduce redundant traces, partial order reduction techniques, which exploit representatives of each equivalent trace class, are utilized to elevate the trace space exploring problem. However, most of these techniques usually adopt conservative conditions to approximate dependence. For this simplified program, we conclude that this program is safe with regard to certain reachability property if final value of the shared variable y is less than 2. With the conservative dependency approximation, only the transition pair uppercase A and lowercase a are independent, and two redundant traces, pi4 and pi5, are pruned. In fact, many redundant traces are still explored. From this example, we hope to use more precise dependency estimations to explore the trace space of concurrent programs. To make our approach more clear, we firstly introduce some useful notions. The CFG-GP of a concurrent program P is defined as the product of sub-CFG GPI of each thread PI, where LPI and TPI represent the set of locations and the transition relation of PI. L0 PI and FPI is the initial and final locations of PI, respectively. As a concurrent program shown on the left, we can build its two sub-CFG GP1 and GP2 of thread P1 and P2 and obtain its overall CFG GP. For simplicity, we use a subscript I to uniquely represent a combination of thread locations. By unwinding a CFG GP, an abstract reachability tree can be obtained. An ART-AP consists of a set of abstract states and edges. Each state S is a triple, where Bs is the first-order formula over a set of program variables. It denotes the reachable region where all variable assignments fulfill the formula Bs. An IgE is also a triple, where T is the thread transition and Bt is the encoded transition formula of T. And we use the set enabled S to denote the transitions that satisfy the execution conditions at state S. The trace pi is a sequence of state transitions from the initial state S0. When constructing an ART, we can perform the reachability analysis to determine whether a state is reachable. For an IgE in an ART, its successor S' is reachable only if the formula Bt of transition T does not conflict with the reachable region Bs of state S. If S' is reachable, we need to update its reachable region Bs' according to the types of transition T. Two transitions are independent if for every state S, they do not affect the execution of each other, and enabled independent transitions are commutative. With this basis, two traces can be regarded as equivalent if one can be obtained from the other by swapping adjacent and independent transitions. Therefore, partial order reduction techniques need to explore at least one trace from each equivalence class. However, due to the impracticality of checking the independence of transitions for all states, some conservative but easily checkable conditions are usually adopted. As an example, if transitions T and T' belong to the same thread, or one of them writes a shared variable which is rewritten by the other, then they are regarded as dependent. For the example program, only the pair uppercase A and lowercase a are estimated as independent. Thereafter, according to the conservative dependence approximation, we have that the trace pi2 is equivalent to pi4 and trace pi3 is equivalent to pi5. After several rounds of exploration, the error location L13 is reached. Hence, this concurrent program is unsafe. From this example, we can observe that at state S6, the two successor transitions B and D do not affect each other, and both the execution orders BD and DB reach the same state. Hence, they are imprecisely estimated as dependent at state S6. In addition, we also notice that the transition A and any transition T of P1 do not disable or enable the execution of each other, and transition A commutes with any transition T of P1, even if it writes to shared variable X that is accessed by transition B. Therefore, we have the trace pi1 is equivalent to pi2 and pi4, and the trace pi3 is equivalent to pi5, which means we can prioritize the exploration of transition A and print other transitions of thread P1 at state S1. To sum up, the partial reduction techniques that using cross-dependence approximation are low in efficiency because the number of equivalent traces may be explored redundantly. Therefore, we are motivated to reduce unnecessary exploration of transitions by performing more precise dependence estimation of transitions. To achieve this goal, we construct constraint dependency graphs to refine dependencies. A constraint dependency graph is an undirected graph of a program. It consists of a set of nodes T and a set of dependency constraints C. The constraint CTT' is a satisfiable Boolean formula which demonstrates the condition that makes T and T' of different threads depend on each other. To construct a constraint dependency graph, we consider three cases. If both the transitions T and T' correspond to assignment statements, then T depends on T' if the final values of assigned variables of different execution orders are not equal. In the case that transition T corresponds to an assumption statement and T' corresponds to an assignment statement, then T depends on T' if the execution of T' disables the execution of T. For this case, the constraint is obtained by replacing the right successor variable in assumption expression in transition T with the right-hand side of transition T' and then negating the resultant Boolean expression. In the last case, where both the two transitions T and T' correspond to assumption statements, then T is independent of T' since it only reads the values of shared variables. The constraint of them is false, and we do not add this unsatisfiable constraint into set C. From the obtained constraint dependency graph, we notice that some nodes do not connect with other nodes. We refer to these nodes as isolated transitions. We have proved that if a state S enables an isolated transition T and transitions T' of other threads, then for any subtrace pi departing from transition T', there must be an equivalent subtrace pi' departing from T. It means that we can safely delay the exploration of other transitions T' enabled at state S if an isolated transition T is also enabled at state S. With the strategy of prioritizing the exploration of isolated transitions, many redundant branches can be printed effectively. Through utilizing the prioritized exploration strategy, the checking states that have no enabled isolated transitions may be reached finally. At this stage, the dependencies of enabled successor transitions T and T' should be determined. If T depends on T' at state S, then only one execution order will be explored. Otherwise, both the execution orders should be explored. At any checking state S, if the dependency constraint CT-T' of transitions T and T' does not exist, or S does not model CT-T', then T is independent of T' at state S. For example, the transition B is independent of transition D at state X6, since X6 does not model the constraint CBD. With the basis of constraint dependency graph, whether core-enabled transitions at a reachable state are dependent can be dynamically determined. We have proved that all the traces framed by PC-DPOR approach are redundant, and our approach guarantees to remove all redundant traces of two-thread programs. And for the programs that have more than two threads, PC-DPOR cannot always guarantee this optimality. We have implemented the PC-DPOR algorithm on the basis of CP-Checker, which supports the BDD-based reachability analysis. We have chosen 529 concurrent tasks from the benchmark fields for reachability property checking, and to evaluate the improvement of verification efficiency, the comparison of different tools was done against on top 3 scored tools that do not utilize the bounded mode checking technique. Moreover, we also compared the proposed approach against other symbolic partial order reduction approaches in 4 modes. Firstly, the evaluation is done for all 529 concurrent tasks, and then refined for 350 tasks, for which all tools report valid results. As the table shown on the left, compared with CP-Checker 2.1, the overheads of time and memory are averagely reduced to 31.61% and 32.65% respectively, and Eugene Carter can verify more tasks than other 3 tools. From the quantile plots of 350 identical programs, we can observe that, compared with other 3 tools, our approach can effectively reduce the overheads for verifying the 350 tasks. In addition, the time and memory overheads of our tool increase steadily in the last few tasks. This anomaly is mainly caused by the large number of garbage collection and BDD node cleanup operations performed by CP-Checker. We also compare different partial order reduction methods to evaluate the improvement of verification efficiency. From the table, we have that, by utilizing PC-DPOR technique, the number of explored states, time consumption, and memory usage are reduced effectively. According to the area under quantile plot curves, our approach needs less time and memory on the 305 identical tasks, which means fewer traces need to be explored when applying the PC-DPOR techniques. In summary, PC-DPOR is proposed to reduce the trace space of concurrent verification tasks. Our approach prioritizes the exploration of isolated transitions in the constraint dependency graph and performs precise dependency analysis at each checking state to print redundant branches. Experimental results show that the proposed method can effectively reduce the overheads for verifying concurrent programs. In the future, we will further investigate a sound and efficient way of combining the quasi-monotonic competition of MPR and the dynamic dependence estimation of PC-DPOR to achieve the optimality of exploration. For more details, please refer to our paper, Prioritized Constraint-Aided Dynamic Partial Order Reduction from ASE 2022. Thank you for your listening.